Assalamu alaikum. Good evening, everyone. Respective Supervising Faculty MD Shahriar Khan Himel and my fellow classmate. Welcome to presentation Group 1 presentation. My name is MD Mahabubur Rahman and my ID 2353703. Today I will give a brief overview important topic the role of ACR in high voltage direct current power transmission. At first, we know what is high voltage direct current. High voltage direct current is used transmit large amount of power over long distance. The process is simple. Generation power plant produce AC. Transmission AC is converted to DC at the sending end. Distribution DC is converted back to AC at receiving end. The types of high voltage direct current system basically monopolar and bipolar. Monopolar is one conductor with ground. It is normally negative, and bipolar is two conductor positive and negative. The advantage of is high voltage direct current, low loss for distribution above 1500 to 1800 kilometer, no synchronized request required between AC grid, uh, and narrower right of way than AC line. And there are some limitation. There is DC promotion is complex. SCR based high voltage direct current require receiving power com- composition. Uh, then we talk about the core function of ACR. What is ACR? ACR is high power unidirectional semiconductor switch thyristor. Then we know the primary roles in high voltage direct current. Rectification sending end converts that AC power into high voltage DC power. Invention rectifying end convert the transmit DC power back into AC power, back into DC power. Invention then thyristor values. Hundreds of ACR connect in series. Block extreme transmission voltage ending. To explain convert operation in more details, I now hand over my groupmate MD Shahriar, Wasif Shahriar. Thank you.
Thank you, Mahabur, for setting the stage and explaining the fundamental role of the ACR in this system. So now I explain my part. Hello, sir. My name is Mohammad Wasu Shahriar, bearing ID 235349443. I'll be talking you through the technical working principle of the ACR in this specific application. Action switch to the converter circuit. Let's turn our attention to the converter circuit itself, specifically the grid's bridge. To convert three-phase alternating current into direct current at such massive scales, like line commutated converters typically use 6 pulse or 12 pulse greatest bridge topology. And in this setup, the sears are arranged in parallel legs. You can think of them as highly synchronized heavy duty valves They do not just stay on all the time. Instead, they conduct current in a very specific continuous sequence. This sequence is perfectly synchronized with the 50 or 60 hertz frequency of the AC grid. By taking turns conducting the positive and negative halves of the AC cycle, the bridge effectively streets the alternating current into a single continuous high voltage DC flow. And now let's jump in the next slide. And this will be the phase angle control and communication. So moving to the next slide, we dive into how we actually manage this massive power flow through phase angle control and communication. Unlike a standard diode, these conductors as soon as in the it is I think is forward bias, yes, and steer waits for a command. It only turns on when we apply a specific electrical pulse to its gate terminal. By precisely delaying this gate pulse relative to the AC voltage wave, a delay known as the firing angle, or we can control the average output DC voltage. If we want to push more power down the transmission line, we adjust the firing angle. It gives us, in essence, real-time control over the grid, but once an SCR is on, how we do turn it off? This is simple. It is where line communication comes in because the system is controlled to an AC grid. The voltage naturally raises and falls and cross zero many times a second. When our AC voltage cross zero and reverse direction, it reverse biases on the SCR naturally a safety turning, and it's very critical. And applied a next gate pulse. So through synchronized switching and precise the gate phase motor, gate phase is efficiently manage bulk power conversion. To explain exactly why ACR are the preferred choice for the demanding job over other semiconductor components, I will now praise the floor to my group mate MD Likon. Thank you, sir.
Thank you, Asif, for breaking down the working principle of the converter circuit. Hello, everyone, and respected supervising faculty, MD Sharia Khan Himel, and fellow classmate. I am MD Likhon. My ID is 2353932. I will be addressing a fundamental question. Why do we specifically choose silicon control rectifiers or SCRs for high voltage DC current application over modern semiconductor device? The primary answer lies in their unmatched power ratings. When we talk about high voltage DC transmission, are dealing with truly extreme environments. We are not managing few hundred nodes. This system routinely handle hundred of thousands of volts of thousands of amperes continuous current, while modern transistors like MOSFET and IGBTs have revolutionized low and medium power electronics. They simply cannot reliably handle the sheer scale of power required in traditional line commutated converter HVDC system. SCR stand entirely in a league of their own here. They process the highest voltage and current blocking capabilities of any solid state semiconductor currently available. When you need to control the power output of an entire power generation station, the SCR is only device with the muscle to do the job safely. Going to my next slide, we see two more critical reasons for their selection: thermal robustness and simplicity. Because an SCR is manufactured on relatively large silicon wafer, it has significant thermal mass. This large surface areas allows for excellent heat dissipation during heavy continuous industrial load. They don't just handle high electrical power, they physically survive the intense heat that comes with it. Furthermore, their integration into the system is remarkably simple. As we saw the previous section, SCR in this specific application rely on the commutation. This means we use the natural zero crossing of the AC grid to turn the device off. We do not need to build complex, expensive, and potentially fragile turn off curiosity. In the power transmission industry, simplicity equals reliability. Fewer complex components mean fewer points of failure, which is absolutely vital for national power grid. Must operates flawlessly 24 hours a day, 7 days a week. So their unmatched power capacity, thermal educare, and operational simplicity makes SCR the perfect fit for the determining applications. To elaborate the specific advantage these characteristics brings to the system, I will now pass the presentation over ANM Sharia Tanvir Nishat. Thank you.
Thank you, Likon, for explaining why SCRs are chosen for those extreme environments. Assalamu alaikum, sir. My name is ANM Sharia Tanvin Nishat, ID 235374773, and I will discuss the specific systemic advantage that SCRs bring to HVDC applications. Let's look at the first major advantage: high efficiency and low losses. And when we are transmitting bulk power over hundred of kilometers, every single watt meters, the primary benefit of an SCR is the scenario. It is exceptionally low on state voltage drop. Even when an SCR is fully conducting thousands of amperes current, the voltage drop across the device is minimal, typically only between 1.5 to 2.5 volts, because this voltage drop is small compared to the massive transmission voltage. The conducting losses are kept remarkably low. The high efficiency is exactly what makes transmitting bulk power over high distance economically and particularly. Furthermore, this electrical efficiency directly translates into better thermal management. Lower power dissipation across the SCR means less energy is wasted as heat inside the converter station. The reduce this reduce the strain on the cooling systems and increasing the overall lifespan and reliability of the equipment. And the next slide. Move on to our next key point. We have cost effectiveness and fault tolerance. From an economic preservative, SCR-based line commutated converters are highly cost effective for bulk point-to-point power transfer. When building national grid mega projects, the lower manufacturing and installing cost of SCR technology compared to newer high frequency device makes a massive difference in the overall budget. But perhaps even more critical than cost is the systemic fault tolerance. Power grids are accepted to unpredictable extreme events like lighting strikes or sudden short circuits. Um, Short circuits. Uh, SCRs HCRs have an exceptional surge current capability. Uh, they are incredibly thorough and can withstand a massive temporary overcurrents without being permanently destroyed. This this robustness ensures superior grid stability as the system can survive and recover from DC lines faults far better than more firing washing device. Then uh, now to show how those concepts are applied in the real world, I will pass my skin to my groupmate MD Faisal Ahmed to discuss practical examples. Thank you.
Thank you, Nishat, for detailing those impressive systematic advantages. I am MD Faisal Ahmed, ID 23537043, and I will be concluding our group presentation today by bringing these concepts closer to home. To see all of these theoretical concepts in action, we only need to look at our local application, the Bheramara Baharampur High Voltage DC Link. This is the critical cross-border power interaction between Bangladesh and India. Because the national grids of our country, two countries operate independently and are not perfectly synchronized, we cannot safely connect an AC line directly between them. Instead, these facilities utilize a back-to-back high-voltage DC converter station. Inside this massive station, giant thyristor valves built from hundreds of ACRs do exactly what we have discussed today. They take the India incoming AC power from the Indian grid and rectify it into DC. Then the next set of ACR immediately invert that DC power back into AC. But this time it is perfectly synchronized with our national grid. It is a perfect real-world demonstration of ACRs safely bridging two complete different electrical networks. Moving to a summary and conclusion. Throughout this presentation, Group 1 has demonstrated that ACIs are the absolute backbone of high voltage DC transmission. We explored their core roles in electrification and inversion, and how we precisely manage power flow by controlling the firing the angle in Grace bridge circuit. My teammates also highlighted exactly why they are chosen. Their unmatched voltage and current rating combined with their physical thermal robustness make them the only reliable choice for handling hundreds of thousands of volts. Ultimately, ACS deliver the high efficiency, low conduction losses, and fault tolerances required to make modern long distance power grid in reality. That brings us to the end of Group 1 presentation. Thank you, sir, for your time. And that's all from our side.